Now we look at something quite different, and the first thing here is mixing. And by mixing, we are only saying that we are mixing two phases or two streams or two parts of the same substance. So you can take hot water, cold water and mix it. And say, well, what do I want to know? I want to know what is the final temperature, for example. So here we will see that there are some other possibilities also. First, there are two possibilities that we will look at. In one, we take saturated state, saturated liquid, and mix it with saturated vapor. And anything else other than this is what we will look at over here. So what we are saying is that we could have either compressed liquid or saturated liquid or a wet state, and we mix either this and this or superheated state. So we are mixing this with this, or this with this, or this with this. The point is that in this case, when we mix the two and we say that they are at the same pressure, the pressure is constant, then by just putting them together physically, there is no change in temperature or in pressure. We assume that these are adiabatic processes. Q dot Cv equal to 0, W dot Cv is also equal to 0. Changes in potential and kinetic energies are also 0. In this case, this will not be true. It will come to some other state. So let's take for practical example, and then we will see on the property diagram what actually happens and why we are even considering such a situation. The one thing is that if we have, say, superheated steam or any other substance going through this, like say superheated, if we want to control and maintain its pressure, the device to use is a pressure regulator. So it will throttle it, so you can only reduce the pressure and maintain it constant. You cannot increase it. But what if I want to reduce the temperature of this? Then theory will tell you that if you have steam at a certain temperature and pressure, and if it is superheated or saturated, and you want to reduce the temperature, there is either you expand it in a turbine or you expand it in a nozzle, both of which are not practical in most cases. Then the only option left is that it should lose heat to something else, or we should mix something cold with it. So what one does is, if we have superheated steam here and we want to reduce its temperature by a small amount, what one does is that through another pipe, we put in compressed liquid at a lower temperature. So this is at T1, this is at temperature T2. T2 is very much less than T1. We inject very small amounts of this, it comes out as drops, and after a while it evaporates and mixes it and produces superheated vapor over here, whose temperature T3 is less than T1. There is very little pressure change in this process. To inject this, you would have brought it in at a higher pressure than P1, but then it would immediately get throttled, and then this liquid will come out. So what is happening is that if you can control this flow rate here, then you can adjust the temperature over here. So in any process, and especially say in power plants, when you say that the turbine inlet temperature has to be fixed at this value, we cannot just by heating steam produce that temperature. We produce a slightly higher temperature, and then by injecting small amounts of this, we are able to maintain the temperature that we want. So this type of a device is called a de-superheater. And this allows us, in the practical world, temperature control. So there's hardly any power station where it won't have this type of an arrangement before the steam enters the turbine and starts the expansion process. So here what we are doing is, we now have to do the thermodynamic analysis of that. So we make the system boundary here. We exclude all the metal and we say, look, this is only the substance that is coming in. So we have one state here coming in, a second state here coming in, state 2, and a state coming out here. This is state 3. So this is an example where in this control volume, we have 2 inflows and 1 outflow. So the analysis of this will proceed exactly the same way that we have looked at before. We know this is an open system, so we write the conservation of mass as before. But before that, we make all the assumptions that we need to do. We say that first, of course, it is in steady state. Then we say that changes in potential energy are very, very small. The device is very compact. Changes in kinetic energy are also negligible. We do not accelerate the fluid very much here at all. And there is no heat transfer to it. This little whole device is insulated, which means that this is adiabatic. Q dot Cv equal to 0, and there is no work or pumping happening, so W dot Cv equal to 0. So if you do all these assumptions, conservation of mass tells us that m dot 1 plus m dot 2 will be equal to m dot 3. So mass flow rate has increased a little bit, yes. And the conservation of energy, the first law tells us for a control volume that m dot 1 H1 plus m dot 2 H2 is equal to m dot 3 H3. And so if we know states 1 and state 2 and we know the 2 mass flow rates, then there are 2 unknowns left, outflow mass flow rate and the outlet state. So we can use this equation to get the outlet mass flow, and from this equation we get H3, which is specific enthalpy of the final state, and this process we assume is constant pressure. Which means that P3 is equal to P1. And that tells us that state 3, we know P3, and from this equation we calculated H3. These are 2 independent properties. State 3 is completely defined. We can get temperature also and all the other properties. So this is an example where we are mixing 2 things. A similar thing is also done in refrigeration systems and air conditioning systems, where if you want to control the temperature of, say this is the compressor, and after condensing we have expanded it and we want to control this temperature now, there's very little we can do by controlling throttling in this. There's a very small amount of range one can do. The rest we can then do is by taking something from here, putting a flow control valve over there and injecting small amounts of this into a device at this point which controls the state over here. So you can control this and adjust the temperature at the outlet over here. So these are practical things where in reality you don't have a system that will always do what the thermodynamics tells you is done at one state. But in real systems you have to operate at lower capacity, you need to shut it down, you need to start it up, and all of that we need to do in a very safe and a secure way. And so many of these devices have to be added on to make the system practical. It makes the system complicated, but that doesn't matter. Ultimately, when you want to analyze it, this is the way in which we can go about and see, well, what is it that I'm doing it over here. Another example of mixing I'll give, and this is a very common thing which is used in all steam systems, which is called a De-Aerator. This is exactly the opposite of what you get in aerated drinks. In an aerated drink, we take water and compress and put carbon dioxide into it, and that's what you get your soda pop. In a deaerator, our objective is exactly the opposite. That water and water that we drink or comes out of the tap or whatever we have has dissolved air in it. Dissolved air means O2 and N2 are dissolved in it. And that's the reason why fish can survive in water with just that little oxygen over there. In steam systems, if we just take that water, produce steam like we do say in our domestic geysers, then what happens is this: when you heat water, some of this oxygen comes out because the saturation pressure of oxygen for dissolving in water decreases with temperature. The result is some of the oxygen comes out into the gas phase, and then if this reacts with the steel components, it will cause corrosion. And this is something we definitely don't want in a machine like a power plant or even a steam system of a submarine which is powered by a steam turbine, because we want that to last for 20, 30, 40 years. So we need to remove this. And what we do is we just heat the water to a temperature of like 150 to 180 degrees Celsius and allow some of the oxygen to come out. So this reduces the concentration of oxygen in water, and then we get deaerated water, and that is then put through the boilers and the turbines. So what we have done is we put water into a tank, into which we also introduce steam, and this all mixes and collects inside the tank or in an adjacent vessel below this. So water is coming there, and this could be say water at about 130, 140 degrees or 120 degrees Celsius, compressed liquid. Here we put steam. This could be slightly superheated steam, and we adjust the flow rate of steam and water in such a way that what you get here is saturated liquid at 150, 180 degrees Celsius. The oxygen comes out here, and we have a small opening here through which water and some of the steam will continuously keep coming out. So that way what you are left here is deaerated water. So you have mixed compressed liquid with say superheated steam or dry saturated steam to produce a saturated liquid. The equations, everything will be identical to what I have just done, and the analysis of this can then proceed. In vapor power cycles, this is also called a deaerator, and it is combined with a temperature rise. Water came at 120 and it goes out at say 150. This is a deaerating feed water heater. And higher the temperatures that one employs of the steam, less is our ability to tolerate dissolved oxygen in the water. So as you go from 550 degrees Celsius to 600 to 700, we have to remove much more oxygen out of this water than what we have in say conventional power plants. So that's one of the engineering challenges, that if you want to increase the thermodynamic efficiency by going to higher temperatures, your oxygen dissolved in the water has to be brought down. There's a different set of things that one needs to put in place. Okay, there are two examples of mixing that I have given. The one thing that we will look at, okay, we have see what happens on the property diagrams. And I will draw the case of say the deaerator. That's the saturation dome, and what we have is compressed liquid coming from here, heated up to this point, and if nothing would have been done, this is constant pressure heating, so this line will go off there, and then it will go there, and then this will go there. And we are mixing this with say superheated steam at the same pressure or at a higher pressure over there. So we brought this in contact with this, mixed it up, and we got saturated liquid at this state. So what is the process that these followed? Well, we cannot in any way get back the original states without putting in extra work or heat or both. So these are completely, hugely irreversible processes. And this one comes down to here, and they come up to this state. If it was this state, it would have again come there, but you might, if you want to show it this way, that dotted lines coming there, that's okay. But even if you should just join it here and show it by a dotted line, because it's an irreversible process, that's also okay. So that's what we are doing here. In the case of the de-superheater, what we did, we had a state over there, a superheated state here, and we mixed water with it, which was at say this state, to produce a state which is at the same temperature, sorry, the lower temperature but the same pressure. So we came from 1 to 2 by mixing things. So we moved from here to here and there to there, but in this case we have moved from there and here to this place. One thing that we had listed there, what happens if you mix two saturated states? For example, we have dry saturated liquid in a vessel here. So this is a vessel in which there is only x equal to 0 at this condition, say pressure P1 or temperature T1. Then you have another vessel at this state where x is equal to 1 at the same pressure, dry saturated vapor. And now we mix the two. It is adiabatic, there is no work transfer involved in this. We say just have a valve in between that which was opened up, it got mixed, and the final state of the mixture was wet. So this could have come somewhere over here. Here, there, wherever it may be. So the question is this also reversible or irreversible? And one can argue that, look, if I have a vessel that you took all this mixture and you have put it in another vessel and allowed it to just stand there, we know that by gravity, the liquid water will come down here, the vapor will stay up there, and if we can just take this thing out, we got saturated liquid. We take this out, we got our saturated vapor, and so we got back our initial states. In some sense, this mixing of saturated states is a reversible process. Okay, it doesn't produce a new state in the sense that pressure and temperature are different, but we just produce a mixture where the proportion of saturated liquid and saturated vapor, they are different. So that was about the mixing of saturated states. And now we do the opposite of those things by looking at idea of separation. And separation basically means that we have a wet state and I want to separate out the saturated liquid and saturated vapor. An example where we really want to do this and do this most certainly is a nuclear power plant. So what happens in a nuclear power plant is that we have, say, we'll show it on the property diagram there. That's the dome. And in nuclear power plants, the steam produced by the nuclear reactor is at a state like this. It's a dry saturated state. This is the state at which we introduce it into the turbine. So say this is the turbine. There is a shaft which is producing power. We got state 1 over there, and we allow the steam to expand in this, and we take it out at state 2. Now what happens here, that because it is dry saturated, the states in which the turbine will expand will all be along a line which is like this. And what it does is that as you keep going down, the dryness fraction keeps getting worse. From 0.99, 98, 9, 0.8, 0.7, 0.6, something like that. Which means that the amount of liquid flowing in a turbine is increasing, and this is largely dispersed at very small drops. And they can go and hit the blades. They don't follow the same expansion law that vapors follow, so that design and engineering of this type of a machine becomes practically impossible. So what one does is that we say that, okay, I can make a machine and I will have exit dryness fraction more than say 0.9. So I can design a turbine and it's reliable up to this point. So at 0.9 we take it out. And then what we do is we separate it. So that this here, the liquid goes into this state, the vapor goes into this state, the mass fractions are less now. If it was 1 kg per second going in, now we have here, say, depending on the dryness fraction, it will be 0.9 kg per second here, 0.1 kg per second here. So this we have put into a device, and this is either separating by gravity or by inertia. But you just rotate this whole thing, the droplets will by centrifugal action go outwards and the vapor will stay inside. So in this we get the liquid coming out here, x equal to 0, and out here we get x equal to 1, dry saturated vapor, but not the full mass flow rate. We then take this and introduce it into yet another turbine and expand it further. And if you want, we can connect these two shafts together, and ultimately this is connected to a generator. So that device is called a separator or a moisture separator, either of these words. And how do we look at the thermodynamics of this? Well, this is a system that we can say that this is the system boundary, and this is of course an open system. So we apply the control volume approach. This is state 2 coming in, state 3 going out here, state 4 going out over there. We assume steady state, no change in kinetic and potential energies. It is a small device, no heat transfer. So Q dot Cv equal to 0. We didn't put any work in it. W dot Cv is equal to 0. And so the conservation of mass tells us that m dot 2 is equal to m dot 3 plus m dot 4. And conservation of energy tells us that m dot 2 H2 is equal to m dot 3 H3 plus m dot 4 H4. So we can then solve it out, and we can know what is the mass fraction coming out at this end. But all of this is happening at constant pressure. That means P2 equal to P3 equal to P4, and the same with temperature, T2 equal to T3 equal to T4. The only thing that we did, that here it was the specific enthalpy became HF, this is Hg, and this was H2, which is in between these two values. So that's the idea of a separator, and what we have done here is just put it through a passive device without putting any work or heat or anything else in it, and by inertia or by gravity we separated the liquid out from the vapor, and we get dry vapor coming out here, which we can then start using again over there. So that's the idea of separation. And like we just saw, mixing, here we did not put any work or any heat. So if we just reverse all of them, we'll get back the state. So this becomes a reversible process. And on this picture, we can say that this state went over there, this state went over there. And that's how we then have two streams from which you do two different things. So that is the process of separation.